All right, let's just dive right in. If you've been following the world of large language models, you know that for the longest time, the big story around efficiency was all about one thing, quantization. But that story is changing, and it's changing fast. Today, we're going to explore why the real optimization challenge isn't about just one tiny component anymore, but the entire system.
And this right here, this has been the gospel for years. The goal seems so simple, right? Just take a model's gigantic weights, we're talking the billions of parameters that hold all its knowledge, and shrink them. Squeeze them down from 16-bit to 8-bit, maybe even 4-bit, just to save memory and get a little more speed. For a long time, that was the whole game.
But here's the thing. What happens when you move out of the neat and tidy research lab and into a massive production-level data center? One that's serving millions of users all at once. Well, the reality on the ground, as it usually does, tells a completely different story. That old bottleneck, it's not actually the biggest problem anymore.
And boom, there it is. This is the sentence that changes everything. See, when you're running at scale, especially with these really long user inputs we're seeing now, the model's weights are no longer the main memory hog. Other, more dynamic parts of the system are taking over. It's kind of like we've spent all our time meticulously fine-tuning a race car's engine, making it perfect, only to realize the real drag is actually coming from somewhere else entirely.
So, if it's not the weights, then what is it? Well, our first culprit is something called the KV cache. Now, this thing is absolutely essential for making these models generate text quickly and efficiently. But, as we're about to see, it comes with a massive, and I mean massive, hidden cost.
So what in the world is this KV cache? Okay, let's break it down. Think of it like this. As a model is writing a story, token by token, it has to remember everything that came before to make sense. Without a cache, it would have to reread the entire story from the beginning for every single new word. Insanely slow, right? The KV cache is basically the model's short-term memory. It stores these key and value states, so it doesn't have to do that super expensive recalculation every single time. It's a speed-up trick.
And this chart right here just visualizes the problem perfectly. Look at the model weights. That bar is flat. It stays the same size no matter how long your conversation with the AI gets. But the KV cache, oh, that thing just grows and grows, and it grows linearly with every single token you add. So for really long conversations, or if you're summarizing a huge document, say 32,000 tokens, the KV cache can actually become bigger than the entire model itself. The very thing we built to speed things up has become the new memory giant. Which, of course, brings us to the big question. If this is the new bottleneck, what are we going to do about it? How can we apply all those clever shrinking ideas from quantization to this new, much more dynamic problem?
So the current fixes are pretty straightforward. We're quantizing the KV cache down to 8-bit values, and yeah, they work, but they're kind of like a blunt instrument. They apply the same precision everywhere all the time. The really exciting frontier is something smarter, context-length adaptive precision. The idea is so simple, but it's powerful. You use high precision for those first few crucial tokens, the ones that really set up the model's core reasoning. But then, as the context gets longer and longer, you gradually lower the precision. This could be an absolute game changer for making these long context models truly efficient.
Okay, so we're tackling the KV cache, but that's just one piece of the puzzle. Modern LLMs use all sorts of other complex tricks to be fast, and one of the big ones is called speculative decoding. And when you throw quantization into that mix, well, things get really interesting and really, really complicated.
So speculative decoding basically works like this. You have a small, speedy draft model that guesses the next few words, and then a big, powerful verifier model that checks its work. Now you're probably thinking, awesome, let's just quantize that little draft model to make it even faster. But here's the system-level trap. If you make that draft model too imprecise, it starts making more mistakes. And when that happens, the big verifier model rejects more of its guesses, which forces it to redo the work. So by speeding up one little part, you can actually slow down the entire system's output. It's a classic bottleneck problem.
And that's why the real solution isn't to just tune one piece by itself. You have to optimize the entire system at the same time. This is what's called joint precision scheduling. As you can see here, we need to find that perfect sweet spot between the precision of the draft model, the verifier model, and even how picky we are with the acceptance threshold. The real goal isn't just a fast little model, it's maximizing the total number of correct words generated per second. You have to tune the entire orchestra to work in harmony.
Now, let's shift gears a bit. We've been talking about memory and speed, these abstract digital concepts. But every single one of these calculations has a real-world cost, a physical cost that is becoming absolutely impossible to ignore: energy.
And this number really brings it home. We have to start thinking in metrics like this: joules per 1,000 tokens. Because when we lower the precision of our models, we're not just saving memory, we're directly reducing memory traffic and how hard the chips have to work, which in turn lowers power consumption and cuts down on the cooling needed in these giant data centers. This is where the abstract world of algorithms meets the very concrete world of electricity bills and carbon footprints. This leads to a totally fascinating idea: quantization-aware scheduling. Just imagine a system that's actually hooked up to the energy grid. When it sees that electricity prices are spiking or the data center is under a really heavy load, it could automatically dial down the model's precision to save power. Then, later, when things are quiet and energy is cheap, it could ramp the precision right back up for higher quality answers. This is how we start building truly carbon-aware AI that adapts to the real world.
Okay, so we've covered memory, system logic, and energy. But there is one more massive piece to this whole puzzle: the chaotic dynamics of trying to serve thousands or even millions of users at once, and how that smashes right into the physical silicon everything runs on.
So, quantization is great because it lets you batch more user requests together. This keeps your expensive GPUs busy, which is way more efficient. But there's a catch. When you start mixing prompts from a ton of different users, the range of numbers the model sees, the activation variance, just explodes. It's like trying to take one group photo where everyone is standing at a totally different distance. You can't find one focus setting that works for everybody. In the same way, a single static quantization scale just stops working well. The solution? You have to be dynamic. You have to recalibrate those scales on the fly for every single batch of users.
And this all leads us to this final, super important concept: algorithm hardware co-optimization. Look, the days of designing software in a bubble are just over. Hardware now has native support for things like 4-bit and 8-bit math. That means we have to design our quantization algorithms hand in hand with the chips they're going to run on. The biggest wins are going to come from designing the algorithm, the low-level code, and the hardware path all at the same time. The software and the silicon have to evolve together.
So after exploring all these interconnected, complicated systems, it's pretty clear that our old way of measuring success just doesn't cut it anymore. We need a new scorecard. We need a whole new set of metrics for what it means to have a successful, real-world LLM deployment.
And here it is. This is the new report card. Instead of just looking at accuracy on some academic benchmark, we need to be measuring these things. How does your throughput actually change when you have more users? How fast is that KV memory really growing? What's the actual energy cost per 1,000 tokens? What's the real rejection rate in your decoder? These are the numbers that actually matter when you're running this stuff at scale.
So if there's one thing to take away from all this, it's that the game is fundamentally changing. The old brute force race for just adding more and more parameters is giving way to a much smarter, more sophisticated challenge. It's no longer about who can build the biggest model, it's about who can build the smartest, most efficient, most integrated system, from the silicon all the way up to the software. The next great leap forward isn't going to come from just lowering the bits, but from rethinking the entire pipeline.